It's really great to be here at USENIX. To be honest, it's great to be anywhere after a couple of years. Having said that, USENIX is really particularly special to me. Going back to my undergraduate days, and one of the very first USENIX meetings was in Toronto. Now, I have to tell you that we definitely did not stay at a resort. In fact, the people that came from out of town brought their sleeping bags and stayed on the floors of graduate student apartments. So we've come a long way. Now we'll see if the clicker works. Yes. So I have to start with, I'm a networking guy, so I'll start with some NACs and some ACs. The NACs or disclaimers are simply to say that some of these slides have a VMware copyright logo on them. VMware was actually kind enough that when I wrapped up my time at VMware, they let me take some. However, anything I say here isn't representing VMware, it's just representing my own thinking. Similarly, I'm working sort of a day or two a week with the National Science Foundation, helping them start up their new TIP directorate, which is kind of really exciting. You should go learn about it. However, again, anything I say here is really just me as an independent researcher, free agent, and not representing the views of NSF. So, don't go making proposals based on anything I say here. In the ACT department, I've just, as Marcos indicated, I've really had the privilege of being at a lot of great places, and it's really not about the places, it's about the people. So I just really want to kind of acknowledge that a tremendous number of people have helped me along the way, have mentored me, provided advice, guidance. I've learned from them, especially from graduate students, interns, et cetera. And through DARPA, one of the best things about that was the ability to get connected to an enormous number of other universities and researchers at those universities. So, if I really put the full logo list of people that I feel like I've, benefited from or that have indirectly had input into this talk, it would be really large. I'd also like to explicitly acknowledge that there's some folks that actually, sort of sat through variations in this talk, and they know who they are. I don't want to implicate them, but I really appreciate the input that they provided. Okay, instead of closing words of advice, just in case I'm running late, I thought I'd provide some opening words of advice. And it's particularly relevant at this time of year when there's lots of interns active. I'm assuming we have a lot of interns here in the crowd, and I know there's a lot of graduate students and interns that are co-authors on many, or primary authors on many of the papers. So Bob Taylor is like, the really great leader of systems research labs historically, and the advice he gave me many years ago was be kind to interns, because someday they may keep you around. Clicker is not functioning, so I'll go back to the if only as a mascot. So with that in mind, I'm going to share sort of some ideas, and this talk is really in that sense aimed at the grad students and the interns, and share some ideas that have, are things that have either been bugging me for a while or things that I really wish somebody would go take care of, challenges for people to take on. One of those is in this, kind of security research space. We've kind of almost evolved a business model of security research, right? Researcher comes up with a new exploit and identifies an exploit path. They find a way to patch the exploit. They go start a startup. The VCs invest. They're really happy. Somebody acquires them, so there's a nice exit for the VC and the researchers. And then basically rinse and repeat. But meanwhile, if you're actually trying to run security at a large enterprise company, you have to kind of buy over 100 products today and then try to put them all together. And all you've really done by doing all that is patched these exploits, and you haven't actually gotten yourself security. So I'd really like to call for and encourage people to try to avoid the incremental work. If you're a reviewer, please, stop, letting all those papers that are incremental through, and try to get people to think really systematically about how to achieve security. I'm not saying we're going to get this with one grand design, But I bet that if we sort of broke this down into 5 or 6 really big problems and people took on those problems, that we could probably make a ton more progress than we've made. Deep learning. Okay, so I think many of us, I really love the results we can achieve with deep learning, right? It's really phenomenal. We can do things that we, for many, many years, just dreamed of trying to do. Now we're not, doing them. They're in production, happening every day. The catch is, I think we've gotten too infatuated with the results to the point where we're losing our curiosity about how the stuff works. And that curiosity, that's the soul of researchers, right? So I think it's really important that people stay focused on not just how does deep learning work, but what are the alternatives to deep learning? It seems, to me, unlikely that this thing that's, consuming just exponentially greater amounts of resources is actually going to be the long-term solution. I suspect that there are people already out there that have the glimmer of the idea of how to do things better. And the catch is that the billions and billions of dollars that are being invested in making deep learning go kind of further and faster and farther is kind of creating a lot of noise that masks the signal. So I'd like to sort of encourage people to be attentive to signals, be attentive to new ideas in this space, new alternatives, because it really feels like this is an area where we've got to make a change. We're going to have to sort of make what we call a left turn to move forward. Okay, so I also really love decentralized ledgers and think this is a great technology. At VMware, we sort of started a whole business around private or permissioned ledgers. I think that's going to be a great business for quite a while. But in the long term, I really think we want to have public permissionless ledgers be trustworthy. And they really aren't today for a variety of reasons. Happy to take this offline. However, the point I think I want to make here is that due to the kind of history of how Bitcoin came about and everything else, we've actually conflated multiple things. There's the decentralization thrust, there's an anonymity thrust, and there's a having your own currency thrust. And all these kind of got bound together. And I'd really like to encourage some folks to think about how could we refactor this to sort of tease those things apart. They don't inherently need to be bound together. And I believe that if we could tease them apart, we could actually move towards much more trustworthy public ledgers. And that would be a great infrastructure for folks to build on in the future. Okay, finally, there's a collection of stuff that is now more than 50 years old. That is actually, kind of the cornerstone and foundation of a tremendous amount of what we in the systems community are doing. And, I really think it's time we moved on. Like, just think about what did computers look like 50 years ago? And many of you won't have seen them, would have to go to the Computer History Museum to get a sense of, what they looked like, what their capabilities were. And does it really make sense that we're still basing much of what we do on these 50-year-old artifacts? So just to call some things out, and I know this is USENIX and not going to be popular, right? Unix, right? Goes back to my undergraduate days. Seems like it's time we moved on. There must be kind of a new approach, and it's really time that somebody propagated that. Declarative methods are something I really, really love, used heavily in the database space. However, our main mechanism for that today is the SQL query language. Again, kind of 50 years old. What's amazing is SQL is getting even more popular today, largely I'd argue because nobody's come up with a good alternative. So I'd really like to encourage people to come up with a great new query language and new ways to use declarative methods. And then most of this keynote is actually going to be about networking, and in particular packet networking. Again, over 50 years old, right? There was a time where we were the rebels upsetting the apple cart of the telephony people and the circuit switch folks. I really want somebody to come and upset our apple cart. So rebels wanted in these spaces. Okay, so as I said, the talk really is meant to be about networking. So the real keynote starts now. I just thank you for giving me the time to just get some of that stuff off my chest. And one of the things I've been thinking about in framing this is the big sweep of time in networking. In effect, we've had sort of three major global infrastructures: telegraphy, circuit switch telephony, and packet switched internet. And operating on sort of basically different structures, different technologies completely. It's pretty impressive how long-lived these things are, right? They sort of are over a century each. Like if you look at telegraphy, sort of over a century that these systems lasted. We think of ourselves as innovating quickly, but the core architecture tends to last a long time. Although we insert what I think of as midlife kickers. We keep increasing and improving a lot of what goes on under the covers in those networks over time. So there's a lot of innovation that's kind of hidden by this sweep. So if you look at telegraphy, and actually there was a system in France called heliography that predated it that was optically based. But if we look at electronic telegraphy, it was a store and forward network. So right there, that tells you that storage was used in the network. And one of the interesting midlife kickers here was when people realized that initially, you had a human being using a Morse code, using a key to tap out Morse code. Signal went over this really valuable wire that was interconnecting the cities, and a human was listening at the other end. And they realized they weren't using that wire very efficiently, right? The wire was restricted to running at the end-to-end human speed. So what they did is, mechanically created paper tape systems. So you could have a whole bunch of humans that were essentially, Morse code keying messages. They got recorded on paper tape, and then those paper tape messages could be squirted down the wire at high speed. So in effect, you had kind of a form of time division multiplexing happening over that wire. They actually also used frequency division multiplexing. So the paper tape was a storage mechanism, and you also saw people effectively using information theory to multiplex more signals onto this. This is where the term baud came from. If we move forward to circuit switching, which was another sort of end-to-end, in this case it was a human at one end of a telephone, human at the other end of the telephone call. This really got going with the invention of the Stroger switch, which was a sort of step-by-step electromechanical switch that enabled the switching of the calls. Over time, we introduced new technology into that. And one of the important things is we added software. Effectively, we didn't change the switch, but you had software control over the switches. So now we're introducing computation into the network, or non-human computation into the network, machine-based computation. We actually later, interestingly enough, moved from having that computation being in-band to being out-of-band signaling with SS7. The reason I mention that is we did a similar thing with the internet. When we moved to SDN, you can think of that as a switch from in-band signaling to out-of-band signaling. The other thing that is interesting in terms of adding digital technology into the circuit switch network, into the telephony network, is we started adding storage. And we used information theory. The information theory told us that we could sample the analog call and create digital samples. And then we'd store them in, oh my God, they were going to have a 1 byte buffer, 1 byte, at the front of each port going into each switch for every subscriber line. So if you added this all up, you might think there might have been a gigabyte of storage being put into all of the United States. And at the time, the decision to do that seemed immense. That seemed like, wow, a gigabyte of storage across the whole country? That was going to be amazingly expensive. But they did effectively put that storage into the network. And that storage meant that much like what had happened with telegraphy, you could now take many, many calls and send them down the same wire. But notice that end-to-end, things had to operate at the same speed. Now, when we move to packet switching, which is the kind of core technology underlying the internet, we really went heavy on adding compute into the network, right? Because now we were doing, instead of doing a computation to set up each phone call, we're basically doing a computation on every packet at every step along the way, right? So huge amount of computation in the network. That's, I think, largely realized. We also added a huge amount of storage, right? We started having packet buffers at the front of those switch ports so that they could sort of absorb the bursts, absorb the packets coming in from the endpoints. Using these kind of two things, we now had a technology that, for one thing, it still worked end-to-end, but instead of being limited to one type of traffic, like telegraphy or telephony, it could carry almost any application that we could digitize. So that was pretty cool. So that was a big step forward. And as I said, we were heavily using storage. We could get statistical multiplexing, so we could now, instead of doing sort of time division multiplexing, we could statistically multiplex many calls onto the wires. We were getting, or many flows onto the wires, getting way better performance and efficiency out of those, expensive long-distance links. There's another value that the storage had that I think isn't fully appreciated, which the storage facilitated rate adaptation. It actually meant that, something connected to the internet that's a low-speed device operating at megabits or maybe even as low as kilobits can send messages to a server in a data center that's connected at, gigabits speeds. And these two things can interoperate. So not only can we carry a range of applications, we have rate adaptation and the ability to interoperate at different speeds, all of this enabled by storage. You're seeing a refrain here, right? More computation in the network, and these are on 100-year timelines, right? More storage in the network. And we actually also added a lot more information theory into the network, because while the internet and packet switching were happening, cellular folks were busy innovating, particularly in the wireless part of the network at the last mile. And in fact, it wasn't just the cellular folks, the fiber to the home folks and hybrid fiber coax folks, also on the wired side. And what they were figuring out is how to get a lot more bits per hertz into the channel using information theory. However, the use of information theory was really constrained. It was basically down at the physical layer and kind of geographically out in the last mile or last kilometer. Okay? But again, you have this pattern of taking advantage of information theory. So what I'm basically saying is the long-standing tools of the networking trade, computation in the network, I'm kind of graying that out because I think everybody here gets that. But I want to emphasize that storage in the network and use of information theory are also really important. So as we start thinking about, like, okay, what happens in the future, we should keep those things in mind. We move to actually a world in which we're not doing end-to-end computing, networking, I would argue. It's pretty much all edge-to-cloud networking. And that's what's really happening, right? The vast bulk of the communication is edge-to-cloud. And these operators of the hyperscalers realized that they could actually design their own networks inside their data centers. I mean, they had the scale to do their own thing. So they could deviate from the internet standard where appropriate and where it helped them. And then they could actually take control of the networks and get their own fibers interconnecting their data centers. And then in order to provide kind of better service to their users, they could push their networks out, extend their fiber networks and their networking technology out till it came very close to the access networks of that last mile or last kilometer. So that creates an interesting situation where we like to think of the internet as this globally connected network with these sort of CADA-style diagrams where everybody's doing the same thing everywhere. But the reality is increasingly the kind of TCP/IP is really just a kind of like a connector, a way you plug things together at key points. And within the access networks, they could do whatever they want. And within the hyperscalers, they can do whatever they want. So there's kind of this gap between the way people perceive the network as this, everybody doing the same thing, globally interconnected, and the reality of what's happening with the traffic. And so kind of one of my themes today that I'll come back to later is that it may be time for some sort of repartitioning of concerns here. So we kind of think through that the 3GPP crowd, they're the ones that do the standards for 3G, 4G, 5G. If you take a look at their stuff, they think they're designing a full end-to-end environment and cloud stuff and everything else. The reality is what they're really great at is doing that wireless part in that last kilometer. That's really their strength, but they're sort of designing in a mindset where they think they're doing the whole thing. The SIGCOMM and Internet Society and community I come from and really love, we think we're designing the whole thing. And there's the hyperscalers that are actually carrying most of the traffic most of the way. Okay, so that's a bit of a spoiler alert that I'm going to come back to this and say that I think the really kind of interesting opportunity that I want to try to encourage through this talk people to look at is computing and networking near the edge at this place where the hyperscalers meet the access providers, because that seems to be a place where there's a disconnect, and that those disconnects represent opportunities to change things. Okay, so as we think about what's likely to be next, it's always good to think about, what are the design constraints? And I think, there are many design constraints for global network infrastructure that are sort of evergreen, right? They're just not going to go away. I've listed them out here. I'm not going to talk about them today. I want to talk about the other questions we should ask ourselves. We shouldn't just get caught up in thinking about the constraints, because we'll likely end up with the same thing that we have today. If we want to think about the future, one good thing to do is to think about what's going to be in surplus, what's going to be unconstrained, because that's going to give you kind of a new currency and a new ability, how you use that currency and how you respond to that change is kind of this new ability to, do things differently in the future, maybe different ways to address the design constraints. So I think a couple things that are going to be in surplus going forward. One is edge capacity. So, if you look at 5G, the promise is gigabits, everybody's phone's going to, operate at gigabit speeds. They're not really going to get there, right? I mean, I think they'll get to tens of megabits, maybe 100 megabit with 5G. However, they're setting the same kind of goals for 6G. So as we think things forward for the next decade, I think we are going to have a tremendous amount increase in the capacity that edge users can feed into the network. To me, this is kind of like a transition that we went through many, many years ago. We had initially 10 megabit Ethernet at the desktop. People were starting to hit the limit of what that could do. And then we dropped 100 megabit Ethernet on them at the desktop. And pretty much nobody could really take full advantage of it. And by the time people started hitting the edge of 100 megabit, everybody already had gigabit, right? I think we're seeing that same transition from shortage to surplus likely to happen about a decade from now, which is the time span at which we all want to do research. For reasons I'm not going to go into the details of, I also think we're going to have a huge surplus of high-resolution sensors that are going to be really cheap and really available. The factories are turning out billions of very high-resolution cameras to go on cell phones today. They're going to keep turning out lots of sensors, and they're going to have to go to other places in the future. So there's going to be lots of opportunity to cost-effectively instrument the physical world around us at very high fidelity and bring that information into the network. So with that change, how will the applications be different? I think we're going to finally see the era of ubiquitous computing that Mark Weiser had envisaged. Now, Mark actually talked about that in the context of comm technology, and this notion that the computing, would melt into the background and would really be essentially in the background doing lots of things for us without us having to ask, right? And without the computer constantly interrupting us, et cetera. Things would just happen. So I think of that as requiring proactive computing and a transition to sort of an environment in which our applications, and particularly these edge-to-cloud systems, right, are going to bring the physical and virtual worlds together, because we're going to have that really great instrumentation of the physical world around us. We're going to bring that together with the information that we already have in our virtual world, and we're going to use it to automatically and proactively anticipate our needs and start taking actions on our behalf. That's the proactive part of this. I've got some examples here, but my point here is it's a different paradigm. So, we still think architecturally that we've got an end-to-end network. In practice, we're using it for edge to cloud. And I think going forward, we're going to be using it for proactive edge to cloud. And we want to think about what we need to do differently. So I think the way we'll do that is take advantage of the tools of our trade, right? So there'll be more computation in the network. Again, that's, I think, pretty obvious. I'm not going to go into detail on that. I think we're going to have to figure out how to take way more advantage of storage in the network than we do today. I've put this chart up here because Dave Chariton did some early work in content routing. I never heard Dave say it's the content stupid. But for those of you that know Dave Chariton, it's the kind of thing he would have said. So I figured I'd put it up there and attribute it. However, there's been a ton of work since that time in this space. To be honest, it hasn't really broken through into the mainstream. This is content-centric networking. It goes under a lot of different names. Scott Schenker wrote a paper with some colleagues, Seeing the Forest for the Trees, that I think calls out some of the reasons it hasn't broken through. But I think now's the time to revisit that. I have some ideas there, happy to talk to people offline. I think there's a real chance to push this through and dramatically increase how we use storage. And when I say in the network, what I mean is, right, between the users of the information, right? Users don't think separately about the network, the cloud, et cetera. They just think it's all the cloud, and it's all going to happen for me. So the other tool of our trade is information theory. And so the key question is, how can we use information theory to move into this future? And my answer there is, surprise! Okay, what I mean by that is actually surprisal. So there's kind of this core tenet of information theory that says that the basic idea here is that the value of a message depends on the degree to which the content of the message is surprising. Okay, so if I send you a book you've already read, no information value. No matter what price I may charge for that book, there's no information value. If I actually send you the result of a coin flip, whether that was heads or tails, and you had it's a honest new coin flip, you had no way of knowing what it would be, that has high information value. So it's kind of bothered me for quite a while that this seems to turn a few things upside down. For example, today we think delivering movies over the internet has high value. That may be true from an intellectual property perspective, but from an information theory perspective, there's not all that movies ever been made. They're all pre-known pretty much, very low rate at which new movies are created actually. So it really sort of, I think, turns around some of your thoughts about what's valuable, what are we delivering, what makes a difference. So a simplistic interpretation of this would be that all the old content, all that stuff that Google's, sort of organized all the world's information, all that's got no value. Well, that really can't be quite right, okay? So I think the more realistic interpretation here is that the way we're going to create value in the future through networks and our computation infrastructure is by fusing old information that's previously known with new information, and that new information is going to be coming from the edge of the network, right? And so what we want to do is be thoughtful about how and where we combine old content with new. And with respect to the old content, we can be super aggressive, right? Off there in the cloud land of doing a ton of opportunistic and speculative computing to kind of pre-compute answers to all sorts of questions that you might need, and using storage, stage the answers close to where the users are. And I think that's a huge opportunity. We do a lot of this today, but I think this is the place we could really systematically take it on. I want to thank Scott Schenker for suggesting I use the term semantic surprise to basically say that we really need to sort of hoist this notion of surprisal and information theory that we currently use kind of just in the corner of the network, largely speaking. It's mostly at the physical layer and out by the edge. We use it a little for compression. But hoist that up to the application layer and really start thinking about, okay, what does surprise mean for this application, and how would that change how I design it and think about it and deliver it? Now, that doesn't mean we should do this independently for each of billions of applications. In practice, at any point in time, there's actually only a small number of different classes of application or classes of traffic that dominate the traffic in the network. So if we really just figured out, okay, go through the Pareto analysis, let's get the top number of application classes of traffic and analyze those, think those through for surprisal, and build the infrastructure for those. And then as new traffic types kind of rise in the Pareto, we can take those on and address those. Okay, so if surprise is the approach, there's a question of where in the network is this going to have the most impact? Where should we leverage it? And my answer there, I've kind of thought about it quite a bit. And I looked at the edge. And I have to say that I think there's some kind of controversy here. There's a lot of people heavily promoting edge computing, doing a lot more at the edge. Personally, I'm a little skeptical about it. It feels like something that's heavily promoted by the network operators, saying, oh, you've got to do this because we're the only, it's the only place you can put it is sort of by our, base stations or by the antennas. So you must do it there. It feels like it's also being promoted by people that used to sell servers into the data centers of enterprises, but now as enterprises move that stuff into the cloud, they need a new market. So, edge is going to be a really big market. So, I've been a little, sort of cautious about how's that going to develop. But edge has some benefits, right? At the edge, we've got low latency. The catch is that we have limited power and limited ability to share the resources, right? You pretty much have to dedicate the resources to the user, individual user at the edge. And that's not always the most efficient thing to do. Now, on the other hand, if you do things deep in the cloud, you've got tremendous ability to share resources, but you have high latency. So I think we want to be is in this Goldilocks zone near the edge, right? And that seems like a kind of amorphous thing. So I'm going to try to put a more specific definition on it. I'm going to sort of argue that near the edge should mean that if you drew bubbles that were about a millisecond speed of light delay, right, propagation delay, you want to sort of essentially put your near-the-edge computation within those bubbles relative to the sensors, actuators, and people that are going to use that information. So you want to basically be able to take advantage of surprise and fusing new and old information within that bubble relative to individual users. And those are big bubbles, okay? Light goes a long distance in a millisecond. Now, the 5G and 6G folks, particularly 6G folks, are actually trying to get down into the microsecond range. Why am I focused on milliseconds? I think the reason is that if you think about what's going to be good for human beings, we would like to improve the latency as experienced by humans. We don't really do anything faster. Our visual system runs at about 13 milliseconds. Our conscious response is way slower, right, over 100. And so if you think, okay, I want to get this down even within 13 milliseconds, I got a millisecond one way, 2 milliseconds round trip, 5x overhead, whatever. It feels like that millisecond bubble ought to be sufficient to get about a 10 millisecond latency. And that's what I'd really like to encourage, is that we take advantage of surprise in a way that allows us to deliver low latency that's basically as good as humans can need, but does it in this realistic, this 10 millisecond, only as good as humans need. Don't try to do better than that. And do it with the best efforts paradigm. And don't even think about, the people looking at 5G and now at 6G, we're trying to design ultra-reliable, ultra-low latency communication. I have a feeling that this can't actually be done. I'd love for somebody to go prove a CAP theorem that says you can't have those both at the same time. Even if it could be done, I don't think real engineers would use it in some of the ways that are being suggested, right? The reasons to go from milliseconds to microseconds, it's basically, if it's not humans consuming the information but machines, and people are imagining that people are going to do things like telesurgery, and they're going to have autonomous vehicles, and they're going to have automated factories, all of which are going to fail catastrophically if you don't deliver the information within microseconds. But that also means they're going to fail catastrophically if the network's not working, if a truck hits the base station, anything like that. So I don't think there's any way real engineers are going to do that. I think what we should do is, instead of sort of trying to gold plate the network to operate at microsecond scale latencies, could we do just a really, really good job of best effort millisecond? Because that would really move the world forward. So I want to kind of encourage that focus. Now, here's some examples of how that could be used. The XCOM people have been working on AR, VR, and there's a key issue there because you really do want to get the response down within those human parameters. Otherwise, people notice the disconnect between what they're seeing, what they should see. They get I, in particular, react and get headaches under those circumstances. So that would argue for putting kind of all the rendering right on the goggles. The catch is, that's power, it's expensive, it's power hungry, it adds weight. So what they're doing is essentially split rendering, where you put some of the rendering near the goggles so that you can always show the human something that's approximately right. And then you put the more detailed, higher resolution, better rendering sort of a little bit deeper into the network. Now, right now, they're putting it only a little distance into the network, but I've spoken with them, and I think they feel like, yeah, that millisecond bubble would be good enough. And the neat thing is, the deeper you put it into the network, the more sharing of those computational and storage resources you can get, and a better job you can do. So near the edge seems to be a really good place for us to adopt this kind of approach where we synthesize what Butler-Lampson's called predictions. Right? You have sort of low latency local predictions that you can produce really cheaply, and you combine them with high fidelity kind of global predictions that you need help from the network to do. And this prediction system, notice, that's kind of a generic approach. You could be using machine learning models, you could be using physics-based models. There's a bunch of approaches that we could use. The folks, Yates and colleagues at Rutgers, are actually starting a new project in which they're planning to use what they refer to as age of information analysis to help this kind of process where, essentially by knowing how old the information is, you can know when something's too late and throw it away, right? Which is kind of very important to fusing the information coming from the two levels of models. Okay, so we can use surprise to do that fusion. What are sort of, I just wanted to look at some of the capabilities we would need to put somewhere between the edge and the cloud. And notice what I'm kind of arguing for here is not that we put capabilities everywhere, but we just kind of find some places. So we just have a 3-level rather than a n-level architecture. And so one thing you're going to want to do that we already effectively do is put a bunch of caching there, right? So that, again, the cloud is cranking away, doing a lot of opportunistic computing, pre-computing things you might need, and packaging them up and putting them in the right places near you. In the other direction, you're going to want to be able to aggregate and filter and compress all of that information that's coming from the edge. It's going to have to, you're probably going to want to move it to the cloud for long-term storage and to, over the long term, improve, right? The information goes from new to being old. Once it's old, you want it to be used to improve the flow back in the other direction. However, the important thing here is you're also going to want to be able to have functionality to fuse the new and the old. So these are the sorts of things you're going to want to be able to do near the edge. So, there are some, if you have that kind of functionality, there's some interesting things you can do, right? One is very smart delivery of the upstream content. The other is you can start thinking in terms of running distributed queries that are at that near the edge place that are going to synthesize the new and the old information. And we'll talk about this a little bit later. But the key point here is near the edge is kind of a magic place to do these things, because I'd argue you're close enough for latency purposes and you're deep enough into the network to get really good sharing of resources. So there's some other reasons for wanting to be near the edge as well. One is sovereignty and privacy. You may have different jurisdictions putting different limits and saying, hey, we don't want information from our state going to that other state. We want you to keep it local, state, country, et cetera. The federated learning people are actually really quite actively pursuing this and looking at this. Lots of opportunities there to do machine learning to get essentially global models without actually having to feed all of the information into a global central core. My colleagues at VMware have done some work to actually take this further by using sort of ensembles of models. So you could imagine that you have a primary model, again, that catches most of the cases and gives you a fast and cheap answer near the edge. And then you have secondary models, and it might not be one. You might have a bunch of secondary models that are designed to capture the sort of more specialized cases based on the information that you're seeing coming in. Now, the other reason, which I alluded to earlier in the talk, is that near the edge is where the cloud providers meet the local access providers. And I think that, as I said, creates this sort of tussle. There's going to be kind of a battle for kind of these control points near the edge, and I think that creates the opportunity for the research community to sweep in and do something really new. This term, Dave Clark, published a paper together with some colleagues quite a while ago called Tussle in Cyberspace, discussing the kind of policy and meets technology issues related to the internet, and I think we're going to see another tussle near the edge. So, with that in mind, there's actually we can sort of see some glimmers of this in two sets of work going on at Berkeley. Some work on essentially introducing a layer 3.5 into the network, and some work on sky computing. These are, not necessarily aimed near the edge. I'm just going to say I think that if you look into them, that they're very appropriate to, kind of overlap with this near the edge tussle and near the edge agenda, and there's basically glimmers of researchers starting to take on this both challenge and opportunity that's coming up where the hyperscalers meet the access providers. Okay, so it's useful to talk about what's the programming model for all this. This is USENIX after all, and I kind of gave this high level, just a sketch of what functionality you might want. Well, to do that, you're going to, what's the plumbing you're going to need to make that possible near the edge? You're going to want to be able to facilitate computation, right? Computation, storage, information theory. At this point, you've got it. So we're going to want to get really good at installing application-level functionality near the edge. And the good news is that, the tools to do that are starting to come along, right? There's challenges to do that securely, doing it with privacy, multi-tenancy. These are all making sure you have good isolation between the tenants. These are all big challenges. But we are starting to see glimmers of this. There's AWS wavelengths giving you some of this kind of capability. I think one of the interesting things is that Cloudflare and Fastly and a few others seem to be selling on using WebAssembly as almost a lingua franca for functionality and computation that goes on between the edge, at a place in the network between the edge and the cloud. So I think we kind of have a lot of the plumbing for this. I do want to go back to a point I made earlier. Let's not get carried away. You could imagine saying, oh, let me drop WebAssembly code at every kind of node along the network. I'm not actually arguing for that in this case. I did previously in my career argue for something similar. But for this particular opportunity, I think we should actually stay focused at that millisecond bundle. So much as I said, let's focus on just delivering sort of 1 to 10 millisecond latency really, really well near the edge. Let's kind of focus on allowing some application level functionality at that bubble within the network and not say we're going to put it absolutely everywhere. So I think we'll make more progress doing that. Now, having said that, there's some things that are missing, right? That just gets the computation. I think we need to be able to think about how we're going to get a lot more storage into those points in the network and mechanisms that are going to uncover the surprise. These are going to be very application-oriented mechanisms to uncover the surprise, at least for the most popular applications. So here's a few ideas there. I talked to, earlier, I said, storage in the network. I think we really need to take another shot at that in terms of content-centric networking type ideas. I think that BitTorrent had a really, kind of very large idea that kind of got hidden in the translation, which was what I think of as a recipe model, right? With BitTorrent, you have the torrent file just kind of describes the object. Somebody can drop the object into the cloud and into the network, and somebody who wants to get that object they don't care. Not only do they not care which copy they got, where they got the copy from, they don't even care if they, where they get the pieces of the copy. All they have to do is go get pieces of the object and assemble those pieces in the right way. So they just need to follow the recipe to pull together the object. I think that there's a lot more that can be gained from following that. We've got an OWL paper coming up here later. Something interesting to me is, although they sort of actually superseded BitTorrent in many ways with a centralized control plane, what's really interesting is that they ended up designing application-specific policies. So this notion of sort of creating application awareness in how their CDN operates, I think is a really interesting move and speaks to this notion of, could we go from there to this kind of surprise awareness for those applications? So I'm excited to hear that paper later. We have, I think, a lot of applications are going to be map and GIS related. So you could imagine that we could develop some infrastructure near the edge that is really good at handling that sort of GIS information. So I think that's kind of a particular challenge people could take on. Somebody should really design the inverse CDN for all of that upstream flow and aggregation, et cetera. I think that's another challenge people should take on. We can do a lot more with declarative methods. And particularly, I think we can finally realize the dream of materialized views. And the concept there is that you can essentially, today, you issue a query, you get your answer from the database. 5 minutes later, you issue the same query to get the new answer. And you keep having to issue the query, get the answer. With materialized views, the idea is you issue the query once, and the answer is constantly getting updated. So imagine if this was happening on a global basis, and the answers were getting updated for you near the edge, and those materialized views are automatically getting fused with the new information as it comes in. I think that's something that we could really design and achieve, and it would serve the purposes of many applications. I'm just going to double click on that a little bit based on some work that my colleagues at VMware, and Mihai's here, can talk about it if people want to catch him offline. Because the underlying concept here is taking advantage of incremental computation. All right, in incremental computation, we have this notion that if you run a program on some inputs, you get an output. If you want to run the program on a slightly different input, unfortunately today, we rerun the whole program and redo the whole calculation. But what if we could just do a delta calculation? Now, unfortunately, that's hard to do in general, but it works for databases. So in the database world, we could actually have this notion of incremental computation. And folks like Mihai and Len and at VMware and others, Frank McSherry, have actually made huge progress on this sort of differential data flow and enabling this kind of vision. Now, here's the one that I think is the really big opportunity beyond that, which is machine learning has a separation of training and inference. And I think we could learn a lot from that. If you think about it from an information theory point of view, what the training is doing is taking all the old information, all the priors, and compressing the heck out of it into the model. And then you can ship the model to near the edge. You take the new information, and that's when you run the inference. That's effectively combining the new information with this highly compressed representation of all the old information relevant to your problem. That seems like a really great model, and I'm wondering what we could do to generalize that design pattern and be able to use it for other types of applications. Okay, so in terms of what's next for networking, to wrap things up, we use the tools of our trade, but a lot more storage in the network, and we hoist the notion of information theory and surprise to the application layer and really take advantage of it in a big way. I think that's a huge opportunity. Just to recap on some of the implications, we need to really, kind of think in terms of application-aware fusion of new information with old information, and doing that near the edge. We're doing this to enable proactive computation, and we need to do that. We need to get really good at hosting that application functionality near the edge. That's the systems part of that. And create, as I said, I don't think we want everybody for every application trying to use that plumbing directly. Create a small set of functionality like that inverse CDN, the materialized views, perhaps that training inference generalized. Create those sorts of capabilities so that people could enable large numbers of applications without everybody having to figure out how to drop their little bit of code near the edge manually. And finally, I think we need to move beyond this sort of 3G, 4G, 5G mindset and really think that as we go into future generations, that we're not talking about networking separate from the computation. We've really got to kind of get a refactoring of the access networks and the cloud and the internet and focus, one way I think to do that is for the next decade, just focus on this sort of 1 to 10 millisecond latency, achieving that near the edge, and focus on this place where the hyperscalers meet the access providers and create a revolution there. So I think it's a great opportunity to refactor networking and enable the next generation of systems and networking rebels. And rebels wanted. Thank you.